Hello, welcome to the 1.16 notes. These are the last notes of this unit, which is exciting, and this is on the intermediate value theorem. And so I don't know if this question is on your notes, but I want you to ponder this for a second and try to think about how do you know. So, have you ever been 3 feet tall? Maybe you're watching this with your siblings and they can say no, but I know all of you, and so I know you've all been 3 feet tall at some point. How do I know? Well, I know that you did not start off being taller than a foot, and I know that you are all taller than at least 4 foot, maybe 5 feet. And so that means at some point you had to have passed through 3 feet to get to the height that you're at now. And so that concept of having to pass through a point and having known that you started off not taller than a foot and now you're at least 5 feet tall, that concept allows me to know that you have been 3 feet at one point. And that concept is what we're going to use today. And so keep that idea and that thought process in your mind. And we're going to come back to it in a second. But today we're going to talk about the intermediate value theorem. And so I'm first going to show you this long definition that might not make sense at first, but then I'm going to kind of write it out, show you graphically what this means. So if f is, so this is the intermediate value theorem right here. So if f is continuous on A and B, and k is any y value between f of A and f of B, then there is at least one x value c between A and B such that f of c equals k. In other words, f takes on every y value between f of A and f of B. I know that was confusing. Feel free to pause this and just try to find meaning in this without me saying anything. So think about it for a second yourself. Okay, so I'm going to break this down a little bit. First, we have this continuous function that goes between A and B, and we've been talking about continuity. It's going to come more into play today, but that basically just means from a graphical standpoint is there's no holes, there's no jumps, there's no oscillation or infinite continuity. And so this is what our function looks like. This is the x value A, this is the y value B. And so this is saying that there is going to be, it's saying that there is a k value that goes between f of A and f of B. So f of A is just the y value that goes with A. That is function notation. So f of A is a y value. F of B is also a y value, but it's just the y value that goes with B. So like if I were to plug in B to the function, I would get f of B out. And it says that there is some value k between f of A and f of B. And if that's true, if there's some value k between f of A and f of B, then there's at least one c value between A and B that goes with, there's one c value between A and B such that f of c, sorry, I'm reading this wrong, this should say c, such that f of c equals k. In other words, f takes on every y value between f of A and f of B. So between A and B, this function, to get from A and B, if we're starting at f of A and we get to f of B, we have to go through every single y value between them to get to f of B. Because this function is continuous, we can't skip, we can't jump. And so if there's a k value that goes between f of A and f of B, this IVT guarantees that there is an x value that our k value goes with. And so that's what this is saying. And I'm going to give you another example with some numbers, and then I'm going to give you another example that's a little bit more conceptual. So this is the same thing, except I plugged in some numbers for you. And sorry, this should say f of 3, and this should say 5. So this is the same problem. It says if f is continuous on 3, 5. So again, we have this continuous function on 3, 5, and 15 is a y value between f of 3, and in this case, f of 3 is 11, and f of 5, and in this case, f of 5 is 20. So 15 goes between 11 and 20. Then there's at least one x value, c, between 3 and 5, such that f of c equals 15. So this is saying there has to be some c value that we're plugging in to f that goes with 15. It is guaranteed that that has to happen. It only makes sense because we're not skipping. And so, in other words, f takes on every y value between 11 and 20. So it has to hit 15 at some point. It has to eat 16 at some point. It has to hit 16.3 because we're not doing any jumping. We don't have any holes. And so that's what the intermediate value theorem is saying. One more time, I'm going to show you an example with some baby growth. So because if you look at this graph right here, let's say that this baby at 1 year old is 29 inches tall. And let's say that this child between 5 years old is 43 inches. And so this is just a graph that kind of displays averagely how a child's height changes within their first 5 years of life. Well, because let's say 35 is between 29 and 49, and because height is continuous, and what that means by saying height is continuous is you can't just jump from one height to the other. That doesn't make sense. You gradually grow. So because 35 is between 29 and 49, and because height is continuous, the intermediate value theorem, what it guarantees, and this is just common sense, it guarantees that at some point between age 1 and 5, the baby was at an age where he was 35 inches. I don't know what age that was. It could be closer to 5 years. It could be closer to 1 year. I don't know where it is, but he had to at some point between 1 and 5 have been 35 inches because you don't just jump over that point. So that's what the intermediate value theorem is saying. And so for the next couple slides, we are going to prove whether the intermediate value theorem guarantees something or not. And so there's always two conditions for the intermediate value theorem. One is the function is continuous, and the other one is that the y value that we're trying to guarantee a c for has to go through the endpoints y values. And so I'm going to show you what I mean by that right now. So first, this says, does the intermediate value theorem guarantee f of c equals 12 on the given interval? Justify your answer. So the first thing we always have to talk about is continuous, because if there's a hole in the graph or there's a jump, we can't prove that it's going to hit every single point. Like if this is the function right here, and this is 3 to 5, and there's a hole right here at 4, I can't guarantee that there's a point at 4 because there's a hole. And so that breaks it. So that's why I have to check to see if there's continuity. And so a lot of times continuity is easy. And this is an example here. So we first want to check, is f of x equals x squared minus x continuous? Well, f of x is continuous. And that is because, and it's continuous at all points. And the reason, because it is a quadratic. And quadratic functions are continuous at all points. And so that's all you have to write down. Like, I know if you write that down, you understand that a quadratic has a domain of negative infinity to infinity. So it's someone from an AP test. If it was a polynomial, so you would say you had like x to the cubed or x to the 5th power, you would say the same thing too. So because it is continuous. The other thing you have to show is 12 between f of 0 and f of 5. And so sometimes people get confused on this notation right here. These are x values. So this is saying, like, is there a c value that goes with 12 between 0 and 5 specifically? So those are always x values. And so if we want to figure out if this is true, we need to figure out if 12 goes between the x values, y values. So that's why we have to find f of 0 and f of 5. So first I'm going to find f of 0. To find f of 0, I just plug it into the equation. The equation is x squared minus x. So I'll do 0 squared minus 0, which equals 0. And then I have to do f of 5, and that equals 5 squared minus 5, which equals 20. And so this condition is also met because 12 is less than f of c, which equals 12, which is less than 20. So this condition is also met. And so because those two conditions are met, because f of x is continuous, and you always have to write a conclusion statement like this. Because f of x is continuous and 0 is less than 12, which is less than 20, the intermediate value theorem, and you can just write IVT. Intermediate value theorem guarantees that there is a c value such that, a C value in 0, 5. So it's specifically in between those x values where f of c equals 12. So there has to be an x value that goes with 12. That's what this is saying. Okay, we're going to go on to another one that is more complicated, a little bit more. So does the intermediate value theorem guarantee g of c equals 4 on the given interval? Justify your answer. Okay, so I'm first going to start off testing the continuity. And so if I look at this function right here, we are concerned about this function specifically between the x values 0 and 3. And so I'm going to look at this function and think, okay, is there a place that there could potentially be a hole or an infinite discontinuity? And if it's a rational function, I'm automatically going to put my eyes to the denominator, because if the denominator ever equals 0, that means that the point doesn't exist. And if the point doesn't exist by the definition of continuity, the function is not continuous. And so the value that could potentially break this function is 2. And 2 is in the interval of 0 and 3, and so I'm concerned about it. And if I were to plug in 2 here, I'd get 0 over 0. So because I get 0 over 0, g of 2 therefore doesn't exist. And so because it doesn't exist, g of x is not continuous. And thus the IVT cannot guarantee g of c equals 4 on the given interval. So that doesn't mean that there is not a c value within that interval that goes with 4. That doesn't mean that. It just means that the intermediate value theorem cannot any longer guarantee that, because at 2 there's going to be an infinite discontinuity, and so that is like basically breaking the function. Or not an infinite discontinuity, a hole. And so that could just like make it so this no longer guarantees it. Okay, 2 more examples. This one is a long one, so just bear with me. Okay, does the intermediate value theorem guarantee a c value where f of c equals -3 on the interval, sorry, I forgot this, right, this specifically on the interval -4, 2. Justify your answers. So we're going to start off looking at the continuity, and we have a piecewise function. And every time we have a piecewise function, life tends to be a little bit more complicated. And so the only place I would be nervous about this function not being continuous is at x equals 1, because that's where the graph splits at 2. And I don't know if the graph is going to like split in 2 and meet at a point and fill that point in, or is the graph going to like meet at a point and there be a jump. I'm not really sure yet. And so because of that, I have to test continuity. And so to prove continuity, the only place I'm concerned about is at 1. And because -1 is between our interval, -4 and 2, I got to make sure it works. If -1 wasn't in our interval, we could keep going. But I'm going to test out the continuity. And so because of that, I have to go through my 3 continuity justification steps. The first one, remember, is does the point exist at 1? So f of 1, if I want to see if it exists, I plug it into this function 1 minus x, because that's the part that says x is greater than or equal to it. So 1 minus 1 equals 0. So f of 1 exists. So one part of continuity has been proved. Now I need to see if the limit exists. And so because I'm concerned about 1, I'll check the left hand and the right hand limit. So the left hand limit, I'm going to use that top function because that's where the values are less than 1. Therefore, they're approaching from the left. And so I'll do 2 minus 1 minus 2, and that will give me 0 because 2 minus 2 is 0. And then we will use the bottom function to find the right-hand limit, but we already know that's 0 because we've already plugged in 1. And so the limit as x approaches 1 of f of x exists because, and this is so much work, but it's okay, you're going to have fun, because the limit as x approaches 1 from the left equals the limit as x approaches 1 from the left. The last thing I have to check is, does the limit equal the point? We already know it's true because we've already done the work, but f of 1 equals the limit as x approaches 1 because 0 equals 0. So f of x is continuous at 1 and thus continuous on the interval. So a lot of work for this problem. So that is the first condition of the intermediate value theorem. If you need to go back through that, feel free to. I went quickly. The second condition of the intermediate value theorem is that -3 goes between f of -4 and f of 2. So the y values that go between -4 and 2. So let's figure out what those y values are. So if I plug in -4 into this function, I'm going to use 2x minus 2 because -4 is less than 1. So I'll do 2 times -4. And I get -10. And then I got to test out, or I got to find f of 2. And I use the bottom function because 2 is greater than or equal to 1. And I'll do 1 minus 2 and get -1. And that works. It would be really sad if that didn't work because we went through all that work with the continuity. But -10 is less than f of c, which equals -3, which is less than -1. And so by the intermediate value theorem, there exists a c value such that f of c equals -3. And I forgot to put this, but specifically between -4 and 2. And so that's that problem. The last two problems aren't as bad and long as that one. So I'm sorry that was so brutal. Okay, last ones. In example 1, we showed that the intermediate value theorem could be used to find f of c equals 12. Now we want to find the value of c. So we know that there is a y value that goes with 12 between 0 and 5. Now we actually need to find that. And so this is really something that you did in Algebra 2. All we're going to do is we are going to use f of c. And we are going to plug in, we know that f of c equals 12, okay? We know that it equals 12 at some point. So we just need to figure out what x value makes this function equal 12. And so I know that if I plug in this value c, I am going to get out the 12. And so now I just need to solve, this is a quadratic. And so if you don't remember how to solve quadratic, this is a quick crash course. I am going to get everything on the same side. So I'm going to have 0 equals c squared minus c minus 12. I'm just writing it up here. C squared minus c minus 12 equals 0. The way that you solve a quadratic, if you're lucky, is you just factor it. If you can't factor it, sometimes you have to use the quadratic formula. But I think what goes into -12 and adds up to -1, and that is -4 and +3. And then I just set both of these equal to 0 because if either of these parentheses equals 0, then if you multiply anything by 0, it equals 0. And I get c equals 4 and c equals -3. I was asked to find a value of c between the interval 0 and 5, and only c equals 4 is between 0 and 5. So this isn't an answer because it's not an interval in the interval, but c equals 4 is. And that is our answer. So that is the c value that the intermediate value theorem guaranteed. Last one, that's just like this. Does the intermediate value theorem guarantee a value of c where f of c equals 5 on the interval -3 for the following function? If so, find the value of c. So it's not exactly just like this one because we first need to prove that the intermediate value theorem guarantees a value, and if it does, we need to find it. So first, we have to check the continuity to guarantee this. It is continuous because it's a quadratic. So f of x is continuous because it's a quadratic. Next, we need to check that 5 goes between f of -3 and f of 3. So I've got to check f of -3 first. If I plug that in that function, I would get 9 minus 30 plus 5, and that comes out to be -16. If I plugged in f of 3, I'd get 9 plus 30 plus 5, and that ends up being 44. And so -16 is less than f of c equaling 12, or 5, sorry, we're working with 5. So -16 is less than 5, which is less than 44. And so the IVT, because of those two things, guarantees a c value between -3 and 3 such that f of c equals 5. And so now we can actually go find that. But why that this would be helpful is because if this did not guarantee it, you could go look for it, but you just might not find it. And so this tells you like whether looking for it is actually worth it if you're actually going to find it. And so what I should do for this is I know that at some point this function is going to equal 5 if I were to plug in c. And I'm going to solve just like the last one. So I'm going to subtract 5 on both sides. I'll get 0 equals c squared plus 10c. And then 5 minus 5 is 0, so I don't need to write that in again. I can still factor these, but I would start by factoring out a common denominator, which is c. So I'd get c times c plus 10. And then I set both of these equal to 0, so c equals 0. C plus 10 equals 0. And if I solve that, I get c equals negative 10. And then 0, c equals 0 is the only one in that interval, so this is our answer. So c equals 0 is our answer. That's it. Thank you for coming along for the 1.16 notes. Have a good day.